I feel like I'm being positive. I guess you're late. Yeah. I'm gonna go to. That's like. Paper copy. So. Initially, I can just leave it. It's off.
Morning. Yesterday we were talking about unit hinting lecture and unit normal lecture. So, unit hinting lecture is a direction lecture because it's a unit lecture and contains only direction information. So it shows the direction of the curve itself. The unit normal lecture is perpendicular to the unit hinting lecture, so it shows the direction of the turn, like is it turning left or turning right and how much it's turning. So explain the direction change of the curve, the possible change. We want to be able to calculate it, and we explained it, the process in the calculation yesterday. The unit intervector is basically a unit vector of the derivative vector. So you'll find derivative of r, which is r prime, and you will find magnitude of r prime. R prime divided by magnitude r prime would be the unit tangent vector. And then from there, because tangent vector itself is a unit vector, so the derivative of the tangent vector as a function, the derivative of the perpendicular to tangent vector, which is why the way we calculate the normal vector is by calculating the derivative of the unit tangent vector and divided by its magnitude. So you basically you use the unit size, if that was even a word. So we convert it into a unit vector, convert the derivative of the tangent vector into a unit vector. That's the normal vector. So that was the process. Let's try it. If you can calculate it, let me know your answer. If you cannot, I'm probably gonna show you the process on the board. Thank you. That's right. The number one thing is that we rule out C because C is not even a unit vector. The unit normal vector or principal normal vector that we're looking for has to be a unit vector. So at least C is not right. All the other one, they have to be perpendicular to the direction of the curve. So if it's not perpendicular, then we know it's wrong. We are. Let me show the process so you kind of see this. So when we're trying to think about exactly how we're going to calculate the normal vector, and that's going to dictate how we go ahead and do it. So we're going to have a plan. So based on what we're talking about yesterday, the curve will have a direction. And that direction can be explained by simply finding the derivative of the curve. So our is the derivative of the original position function. And we turn that into a unit vector, which could be a slightly shorter version of the same direction, but make the length, change the length of that arrow to a length equal 1. And that will be called the tangent vector, the unit tangent vector of t. The initial letter of tangent is t. And then we know that the t function is a unit vector. Therefore, the derivative of this function, with t being the variable, the derivative of it will be perpendicular to itself. So you would be able to find the perpendicular vector of it if you find its derivative. But unit vectors, unit vector value function might not have a unit vector derivative. So this t prime that you test out, it is definitely perpendicular to t, but it's not having a unit. It might not be unit vectors. So we turn that into a unit vector. That's the one we call a normal vector. That's the one. That's the process. Differentiate, make it a unit vector, and differentiate again, make it a unit vector. Let's look at the process. The original vector, the r function. Write it invisible. R of t is 3 cosine t, 3 sine t. So the first thing is we find the derivative. This one r prime t. Right, derivative cosine is negative thing, so it's negative sine t. Derivative sine is cosine, so 3 cosine t. And that is the derivative. And you have a new answer. That's right. Maybe you guys already, no, that's not right. If you have finished, you want to submit your answer, you can try.
I was just trying to write down the equation, but
Okay.
there's that font thing in the way.
Okay, let's go back to that page. If you did a little bit more calculation, already had the answer. Can't submit the answer. Nora, that's not the one. No. So let me try to finish we got our derivative now. Now it's time to make a unit vector, and then you can see that if you square the x value, square the y value, you find the magnitude actually equals 3. So we divide both of them by 3, and that will be the unit tangent vector. So the tangent vector is equal to, let's skip the part of finding the magnitude. So that will be negative sine t and cosine t. Now this is a vector that has a magnitude that equals 1. Now it's time to find the normal vector. The tangent vector right now is a vector that has only a length equal to 1. So that's a unit vector. So if you find the derivative, it will be perpendicular to tangent. So t prime of t would be perpendicular to, so it's negative cosine t. Derivative cosine is negative sine t. Okay, that's what we have. Derivative times cosine, derivative cosine is negative. So we have the derivative of the tangent vector. And then we can look at the magnitude of this vector, and we will try to convert it to a magnitude that equals 1. However, this t prime, the magnitude of t prime is 1. So that is already the unit vector. So if it's already unit vector, we don't have to turn it into a unit vector. So that's already the nt. So nt is equal to negative cosine t and negative sine t, since the magnitude of t prime equals 1. So there's no necessary division happening here. So that will be the answer to the question. Hope that kind of clarifies the process. And now try to make it smaller. So we can see the entire process. Let's go back to that page. Answers to the question should be that kind of explain how do we calculate the unit normal vector. I think I had 21 answer. That should be everyone attending. That's today's attendance question. If you came in late or if the board did not show your name and has a reported answer, then you should let me know after class. We can always update the attendance by the class. Okay, any homework question? So far we have section 1, 2, 3, 4 for chapter 11. Chapter 11 is a shorter chapter. Today we're going to try to go through chapter 11, 11.5. So theoretically, we're going to finish chapter 11 today. That means within 1 week, I try to make every homework, give it 1 week so we finish the homework. So that means by next Wednesday, we should have finished all the homework for chapter 11. So my plan will be schedule the test 2 that was over chapter 11 for next Thursday. Is that okay? So let's try to finish. I try to finish the chapter 11 and 10 a little earlier because we wish to, so then the scheduled time will be next Thursday. That will be September 18th. We're gonna have our test 2. Okay, so test 2 is over chapter 11. Didn't write anything in there, but that should be visible on the schedule. So for week 6, next Thursday, we're gonna have test 2 in class. Okay, so let's try to make sure that we finish all of our chapter 11 homework before that. Right now, I could reopen 11.1, so 1, 2, 3, 4, 5. They're all online, and the main thing is section 3, since that's the part we start talking about motion. 2 is the calculus with any vector value function. Section 3 focus on calculus with motion. With motion, we have tangent line, and and then we have velocity and acceleration. And with that, we can start talking about the other vectors, the charge and the direction, and the decomposition of the acceleration function. So these are related to physics. I don't have a lot of questions assigned on them. They're still part of the application of calculus into other sciences. Question. All right, I want to make sure I announce that so we know it's coming up next week. If you have any homework question that was hard, we can talk about it before we start section 5. Any questions? Okay, so let's start with section 5. The section 5 title is called arclength, parameter, and curvature. The arclength parameter is a new parameter. We already have a parameter in all the vector value function. The common notation for the parameter is t, because we often use our vector value function to represent motion. So t as the initial letter for time is a convenient notation. So the arclength parameter is another parameter. T is a parameter, but we could use other parameter, or you can say t could be represent other things. Right now, t could be representing time, but the arclength parameter is saying maybe we don't use t to represent time. Maybe we can use t to represent length. So when the distance is 1 and distance is 2, distance equal to 3, where we are in that location. So it's like you're driving on the highway, you drive 1 mile where we are, and then driving 2 miles where we are. If you drive 50 miles, what was the location? The location is a vector value function, which could be 2-dimensional or 3-dimensional. But your parameter indicated how far you go along the path. So that's the purpose of the arclength parameter. It's just a new parameter. Or maybe it's a version of the parameter. All right, with the arclength parameter, we can talk about definition of curvature. Curvature is how much a turn that we have. And so far we talked about speed and then velocity. Velocity contains speed and the direction. So when we try to separate direction and speed, speed is basically the absolute value of the velocity, which is simple enough because the calculation magnitude is a one variable function. However, direction is not, and we sometimes want to know how much a turn that we're turning. So curvature, when curvature is large, we're making a big turn. If the curvature is small, we're making a small turn. If the curvature equals 0, that means we're not turning. That means we go straight. So curvature is a nice way to have a quantitative measure of the how much turn that the motion is making. All right, so let's look at the definitions. Let's start with definition of the definition of the arclength parameter. Here's illustrating the same thing that we were saying. This is actually for our example. The example that we had in the last 2 sections was about a parabola that was like an angled parabola. So this is like a t squared minus t, and this is t squared plus t. It was the x value and y value for the position. So you can find the derivative, and the first derivative goes 2t minus 1 to t plus 1. The second derivative is 2, 2, which means we have a common velocity that goes already in that direction, 2 unit up 2 unit. So that's why it's being pulled, even though it was originally moving to down to the left, but then something is pulling it back up, so it went back up again. So that's the motion and the acceleration affecting the motion. But you can see these 2 pictures are different. The first one was using the original parameter, which is t. So if t equal to I think was equal to -2, that we're at 6 t squared minus t equal to -2. That's 6 and 2, and then t equal to -1, t equal to 0, t equal to 1, t equal to 2. So those are all the location where it's calculated with appropriate t value. You can think of t as time, like time -2 times -1 times 0 times 1 times 2. But over here on the right, if x equal to 0, that means you are at distance 0. So that means at first you're here, 1 mile here, 2 miles there, 3 miles, 4 miles, and so on. So these like really representing the length. See, at the space of the point on the right side graph, the space are the same because we're using a completely different set of function. So how are we gonna represent it? How does the function change? So let's first start with the definition. Now we already have the arclength formula saying you want to find distance from one point to another. For example, from time 0 to time t, how far do they travel? The calculation is the magnitude of the derivative function. This is actually the speed, right? Absolute value magnitude of the r prime represent the speed function. So we're integrating the speed, which then give us how far we travel. So that's the formula for arc length from 0 to t. So now we decided to represent that in letter S. So what does it mean is S is the distance that we can travel from 0 to t. So then S here become a new variable. How does it become a variable? It gives us the connection between the variable t and the variable S. So it will be this formula. Okay, it's a definition. It is also a formula that shows you how can you calculate S given t. In reverse, if this formula, after we calculate it with the actual function, if this formula has a inverse function, which allows you to calculate t with S in there. So right now is S being calculated with t, a formula of t. T being the upper limit of the integration, but t is part of the formula anyway. So you will be able to find out representation of t using S, and that allows you to convert your original formula of the function into formula with S. And let's look at how it works. I guess I have this solution on this page, so we can actually copy off the question and start work from the beginning. You don't see the answer, how it looks like. Okay, so here we have a curve. This is actually a straight line, a line. Because you see 3t minus 1, 4t plus 2, they're all in degree 1 whenever all the parameters are in degree 1. It could be a line in 2 dimensions, or it could be a line in 3 dimensions. Right now it's a 2-dimensional line. You can actually draw it on the xy plane. That line, right now the t is a given parameter, but we don't know whether it goes, they call how long it is from 0 to 1. But we're going to try to write a formula to find out how we convert it to a arc length parameter. So we want to switch the parameter from t to s. So we're trying to create something that goes rs. So we wish to have a formula that s is the length. And then we can find out a position when s equal to 1, s equal to 0, s equal to 3. So we want to switch out our parameter to the arc length parameter. So how do we do it? If you are trying to create something in relation to s, or in the representation in s, then you have to find out the s relation with t. Now, according to our definition, arc length parameter s is equal to 0 to t, the magnitude of r prime u. I was writing on the definition. This is really a piece of calculation from time 0 to time t. But nonetheless, that's our formula. If we were to apply the formula, we have to have a function ready. In the formula, number 1, we need to know the derivative. Number 2, we have to switch out the variable because we're integrating, and integration has an integration variable. In the definition, it was the u and the u. The reason that we use the u instead of the t, because t is being the upper limit there. So this is not integrating from 0 to 1 or 0 to 5. It's 0 to t. So this t is a variable. So that's why we can't use t as a variable in the integration. So we have to switch out to a new variable. U is a common variable, so we are out of letter to use. So let's try to write it. So now we'll start with the r function. The original function goes like this. R t, it's equal to 3t minus 1 and 4t plus 2. That was the original function. So we're switching out the variable to u. So then we are r u, because we are getting ready for the integration. R u equal to 3t minus 1 and 4t plus 2. I realize that when we try to find derivative, the derivative is constant, right? Derivative of this will be r prime u. That's what we need in the calculation, in the formula, in the definition. r prime u is equal to root of 3u. It should be, since I changed the variable, I didn't finish changing the variable completely. 3u plus 2 4u plus 2. But anyway, the derivative is 3, and the derivative of y value is 4. So we end up having a constant number for the x value and y value. Here is the magnitude. The magnitude will be magnitude of r prime, because the u or t is constant. So it's square root of the summation square for the component. So it's going to be 3 squared plus 4 squared, which is root 9 plus 16 squared is root 25 is 5. There we have it. So we know that the inside part, this is 5. So our integration, now we're ready. Now we have our magnitude calculated. Let's be magnitude. It's the integration 0 to t. And now it's 5, so it's 5 du. Now if you integrate 5 as a number, the anti-root of 5 is 5 u. Then we have to put in upper limit and lower limit to the u. So after the integration, u equal to 5 and u equal to 0. When u equal to 5, 5t. Upper limit is not 5, it's t. It's a variable integration limit. So putting t as u, we have 5t. Okay, so the whole process, the ultimate goal is to find the relation between s and t. So this is how it is. After calculation, s equal to 5t. That's the relation, 5 times t, s. So they're not equal. So that means the original definition, the t is not s. But the relation is clear that you can calculate t. You divide both sides by 5, t for s over 5. S divided by 5. And then we bring that back to the original formula. So then the original formula, RT, is going to be how we enter and determine the RS. So RS is equal to, you substitute, basically it's the same function, but the T is supposed to equal to S over 5. So those T are replaced by S over 5. So it looks like 3 over 5, 3 times S over 5, 3 over 5, S minus 1, and then 4 times S over 5, so 4 over 5, S, and then plus 2. So this is, it's called parent, what's the intonation of the word? Parameterized, is that even a word? Sounds very tongue twisting, but basically we're switching to a new parameter. So then the parameter actually is the arclength parameter rather than the original parameter t. So that's the new function. That's the answer to the question on the textbook. In the textbook, they're more organized, but I want to derive it from the beginning so you kind of see the whole purpose of it. So the original formula for S equal to 0 to T R U D U, F's value, magnitude. That whole point is to find out how was the S being related to T. So then for now, we know that S equal to 5T, therefore T equal to S over 5. And therefore those T can be replaced by a formula of S. And when the formula of the original formula becomes something that has S as a variable, and then we finish our conversion. I hope that kind of makes sense. Any question? All right, so that was one. Let's see. The rest of them are discussion that are conceptual. So let's try to look at the picture that I'm gonna show that they are essentially the same thing. The first one that we had was and again, 3t minus 1 is 4t plus 2. Okay, 3t minus 1 and 4t plus 2. As you see, it's a straight line, and we can make it longer. -3 to +3a. Okay, and then let's try again. The one we had is 3/5. We basically divided by 5 times t and then -1. And then 4/5. And then times t plus 2. We did a substitution of t/5. Right. So I was using the same parameter though. If we do -3 to +3, it will be shorter because it's literally represent the distance. You can try zoom in and let's say we make t from 0 to 1, and that's exactly 1 unit. All right, and then you can make t from -1 to 1 as 2, 1, 2. See, this is how long 1 is. You can compare the distance here. This is 1, this is also 1, that's 1, that's 1. So you can literally see that when with every unit change of the t is 1 unit change to the original curve, to the line. But this one is different. This one when you go, this is magnified. If you go from 0 to 1, it doesn't look longer, right? T equals 0, so here T equals 1 over there, it's way longer than 1. That's kind of the purpose of converting to a arclength parameter. That parameter is convenient and helps. Okay, let's go and try the homework question number 1. That's one of the conversion question. What we see here is this. Okay? The question says, find the arclength parameterization of RT. Meaning now we want to rewrite it so you can still represent the same curve, but we're going to change the variable. So here are the process. So we would do similar things. Okay, number 1, you do the same. You define the S in order to determine, hey, how do I convert it? So basically it means the original question had variable t. Now we want to change the variable S, namely the arclength parameter. So then we need to find out how is t related to S, so we can substitute the idea. So S equal to integration 0 to t, and that's where the t is. And here we need the magnitude of our prime, and then e u. So that obviously means we need to find the derivative. Derivative of this function will be, there's a t in here, there's t in here, because there's 2t function of t multiplied. We have to apply product rule. Using the product rule, derivative et is still et, and multiplied by sine t. Product rule is f prime g plus f g prime. So plus this time we're going to keep the et. We'll find derivative sine t. Derivative sine t is both sine t. That's all the way. All right, and then the derivative second one is the same thing. You do et, derivative t, et is et, multiplied by cosine t, and then plus keep the et, find derivative cosine t, which is negative sine t. So the negative sine t is negative et sine t. And lastly, we find the derivative 2et, which is still going to be 2et. So that's the R prime, and we can kind of expect some complexity because we need to find the absolute value. So we're going to go ahead and say if we can combine things before we integrate it. So absolute value of the R prime. It is a function, but S is a variable part. Magnitude is measure of square. That looks long. So to make it easier for finding the magnitude, I'm just going to try to get the common factor et out of it. So get et outside, and you have sine t plus cosine t, and then cosine t minus sine t, and this is a 2. Right? The shorter the representation, the easier when you write it up. So let's say now that R prime is less long, let's try to find the magnitude. The magnitude of et will still be et. T is a positive number. That's multiplied, and we multiply by the magnitude of the vector component. It will be sine t plus cosine t squared. That's my shorthand for sine and cosine. Plus the second component is cosine minus sine squared. And then we plus the 2 squared, which is 4. All right, so now we can kind of see the difficulty. There's sine, there's cosine, there's stuff. So realize that this is sine squared plus cosine actually equal to what? This e multiplied by under the root. We have sine squared, I'm gonna write it out, sine squared t plus 2 times sine times cosine. It's long, so I'm gonna have to write the shorthand still. And cosine square, then plus cosine square minus 2 times cosine times sine, and plus sine t squared, and then plus 4. Okay, excuse the SINCOS, because you know how long they are if you write the whole thing with the full name of the function, so see that. But because we aim at trying to determine the relation, there's a 2 times sine times cosine, there's 2 times negative 2 times sine and cosine. They actually cancel. Okay, and then we also have sine plus sine squared plus cosine squared, which equal to 1. And then the cosine squared plus sine squared, which also equal to 1, so it's 1 plus 1. And then plus 4. Okay, so literally everything under the roots actually equal to 6. So that's really root of 6. Also have to multiply by ET. Okay, so that is after we simplify the whole magnitude of our prime thing. You see this kind of formation of function a couple times in the earlier section. So now we can kind of see how we can handle them with a more concise way. Anyway, the final answer to this is a simplified version of this. Now we can go back and start calculating our arclength parameter. This is equal to 0 to t. Now we know that absolute magnitude of our prime is equal to e to the t, but we have variable u, so e to the u root of 6 du. Root of 6 is the multiplied number, it's coefficient, you bring the root of 6 outside. Integration e to the u du is e to the u. Like derivative of e exponential function is exponential function, and integration of exponential function also is itself, unless variable has any coefficient. Now we have to deal with the chain. Right now there's no worry. So we got 0, we got t. These are the u part. So you're gonna have root of 6. Okay, and then e to the t replace the u. Also 0 replacing u, that will be e to the 0. E to the 0 equal to 1, so that's e to the t minus 1. So there we have it. So the s is equal to root of 6 e to the t minus 1. We have to substitute the t. So this equation is not enough to finish everything. We have to solve for the t in our relation. So we have s equal to root of 6 e to the t minus 1. To solve for the t, let's divide both sides by root of 6. So s over root of 6 is equal to e to the t minus 1. We then add 1, so s over root of 6 plus 1, which equal to e to the t. And how do we get t by itself? You know e to the t equal to number, and how do we get t by itself? Natural log. Thank you. So t would equal to natural log of s over root of 6 plus 1. You could use multiplication, find a common denominator, use division, turn division into subtraction. So there's a lot. Some simplification you can do on this to get that natural log a little bit less complex. But we can also just simply substitute all those t. Okay, and then another thing is we have the e to the t equal to this, right? If you need an e to the t, it will equal to this already. You only have to get t by itself for those sine t equals sine t part. So that will be the conversion. We copy the functions. You can see we can write the function out. Right, so that's the original R, and how do we write it? We have a e to the t, which is this. So you go 5, that's s, not 5, s over root of 6 plus 1. Right, writing multiplied by sine t. The sine is going to be sine natural log of all that. And then e to the t again times cosine, and then natural log, and then times 2 times e to the t. This is e to the t. So this is kind of messy way to write it. Let me try to write it in here. We have the s divided by square root of 6 plus 1. Okay, multiplied by sine t. Now the t was natural log of that's the e to the t. So that would be the natural log part, right? So this is, and then we have the same thing, and then cosine, and natural log, and this, and then 2 times the e to the t. Oh, I put them all in the same spots. Yeah, separate spots. That's the e to the t, 2 times e to the t, and that comma, we already have a comma. Yeah. Okay, let's see, if we submit there. Had one too many. Okay, so this is how, after we enter it, that's the e to the t that we solved. This is natural log of e to the t, or natural log of this. So this is really the t that we solved. That's the e to the t. So these are being applied to the substitution to get our new function. Any question? Are we okay? Right. Let me know if you have any question. I hope that I kind of explained the whole process. Let's try to make it smaller. So you can see the entire process. We calculated the derivative of r prime and then factor out the t to get ready for the calculation for the magnitude. Do it with magnitude calculation. I try to make the sine equal sine less cumbersome to write. If that's still confusing, you feel free. If you're working paper, you can write sine equals sine. Me, I was using the computer mouse for the writing to try to make it shorter. So they're being simplified to a shorter formula. And then after the magnitude, it's easier to integrate. We bring that here for the integration. So if we integrate this, change variable, finish integration, and then now that's the relations. S equal to a formula with respect to t. Then we solve the t from there. That will be getting ready. This is our t. That's our e to the t. These are the two functions we're using substitution. So the original function have t and then e to the t. So if you got a formula for both, substitution is easier. Any question? That's the first example we did it is to change the way we do parameter to make our works. The rest of the question are curvature calculation of curvature. So let's try to go ahead and start talking about curvature. Now, the reason that we have to introduce arclength parameter before we explain curvature is because our book defines curvature in a way that's related to the arclength curvature. There are books that defining it slightly differently, but most of them have to go into the basic meaning of because the curvature kind of related in a short time and short distance. Like if you are traveling 5 meter, within that 5 meter, are you going to do this or are you going to do this? So the distance is more meaningful instead of time when we talk about term. Okay, so here let's talk about the implication of it. Our definition for the arclength parameter, it says st equal to 0 to t arclength u magnitude du. So we're defining this parameter using an integration. according to the fundamental theorem of calculus, that also means any function that defined by integration have its natural formula for the derivative. So the derivative of s, if s is considered a function of t, derivative of s is the inside part. That is a derivative. So defining the function with integration, meaning that this is a derivative. Like integration is trying to find any function that has this derivative. Therefore, this function itself, the derivative is in that form with one little thing that your variable is t. So your formula of derivative this, but you have to switch that variable to t. So that's why s prime t, the derivative of s is magnitude of r prime t. That's exactly what we have inside the definition of st. So now we have the derivative of the arclength parameter. Writing that into the differential notation is dSct equal to magnitude of r prime, and therefore the derivative of the r prime. So this is our r prime. R prime will equal to the rds dsdt. Because you see the SCT only represent the magnitude of r prime, and then the RDT, the RDS represent the direction of it. So that's the implication of it. Oh, this is following the chain rule. Any question for this? So we're having three variables here. The R, S, and T. Again, the marker. So let me just try to explain what we're talking about here, and then try to see the whole purpose of using this new variable. Okay, so you can think of this as three variables. The R, which represents position, is a vector, and then we also have S and we have T. So relation between R and S, this is where we get the R, ds. Relation between the S and T, ds, dt is rate of change between S and T. So therefore, rate of change between R and T, which will be the R prime. Right? So dr dt equal to ds dt, dr ds ds dt. This is the fundamental reasoning in chain rule. It's a chain reaction between the three variables. Now, since we have this relation, the dr dt is R prime essentially, and then the RDS is the R prime S if we change the variable to S, and then the SDT is R prime, the magnitude of R prime T. Then the bottom rule there is indicating this relation, and then we define something called the division of R prime with magnitude R prime T. That is, we divide R prime T with R magnitude R prime T. That's essentially the tangent vector. So we have R prime S. So following what we have here in this bottom line of formula, we divide both sides of the equation with the magnitude R prime T. So R prime T divided by magnitude R prime T equal to R prime S. Now R prime S actually is the tangent vector that we define in that section. So here we have R prime S, its derivative. R prime S actually equal to R prime T divided by magnitude R prime T, which essentially is by definition the T function, the unit tangent vector that we were talking about in that section. Okay, so that also means that the R prime S actually is a unit vector. And also means that whenever you calculate the derivative of your position function, if the magnitude is 1, then the parameter that you're using must be the arclength parameter. So this is a way to determine, are we using a vector that has magnitude other than 1, or are we using a arclength parameter? So this is how can we tell whether our parameter is a arclength parameter or not. Okay, so let's talk about curvature. On this graph, you see 2 points, point A and point B. at point B, there's barely any turn, but there's a slight turn to the left if you follow the arrow along the path. But then at point A, we see a sharp turn to the right. We are slightly turning left and then suddenly we're turning right. So there's a sharp turn at point A compared to point B. If we want to measure or describe how sharp the curve is, we want to have some kind of measurement for it. That will be the reason that we want to define curvature. This is definition for curvature. Curvature, I guess the notation should be called kappa or K. The curvature included a magnitude of VTDS. So that's really the magnitude of the tangent vector if the if the parameter is the arclength vector. So we mean that the curvature is not the magnitude of unit tangent vector of any vector value function. It has to be the arclength parameter that we're using. So then the T prime will be actually meaningful for this. So then curvature is defined in the way that we have to use arclength parameter. If we use any other parameter T, then magnitude of T prime T is not the curvature. It has to be magnitude of T prime S. Then this magnitude actually represents curvature. Any question? Now, T represents the direction of the curve. T prime represents it's perpendicular to T. To represent the magnitude of that is what we call K. If we remember, the T prime is supposed to be perpendicular to T. So T prime is a vector that has magnitude and direction. Okay, so the direction of T prime should be the normal vector. The magnitude of T prime is now being called curvature. That's the definition. And we certainly wish to have an easier way for the calculation. We can't always do the conversion of variable all the time. So we wish to find some other quicker way to determine or calculate K. All right, so suppose we're using the arclength parameter in the position function. Then according to the definition that we had from last section, T is defined by R prime divided by magnitude of R prime. N normal vector is being defined as T prime divided by magnitude of T prime. Okay, and so if we're using arclength parameter, then the magnitude of T prime would be the curvature, which means the denominator here will be the curvature. Therefore, T prime has two components. The magnitude of T prime is the curvature, which is K, and then the unit normal vector is the direction of T prime, the unit normal vector that we talked about in last section, that is perpendicular to the original tangent vector. And so that's one of the interpretation of it. So K is like the magnitude of that T. Okay, we certainly wish to find out how to calculate it. Here we have an example of a line. You can see 3t minus 1 14 plus, it's the same that we had earlier. The reason we use this example again, because we have done some calculation, we already know how to turn this into the arclength parameters. We can have our RS very easily. Number two is this is a line. We all know that a line has no turn. So theoretically speaking, it should have a curvature equal to 0. So let's calculate it. We already did a change to arclength parameter. So first we have to do a change to the parameter. So instead of T, we're using S. And remember last time we had an example. RS turning into a arclength parameter. It was 3/5 S minus 1, and then 4/5 S plus 2. Now the parameter S equal to 0 is at position 0, S equal to 1, and distance with position 0. Okay, so first we will find the R prime. of S. Okay, it would equal to 3/5 the x component and 4/5 of the y component. Okay, and then the magnitude of this, which would be, we already know it, like the magnitude of 1 because we converted it to the unit fraction. This is also equal to the tangent vector. Okay, and then the curvature is supposed to be, by definition, it's the magnitude of t prime. Right, so that was t. So t prime of s is finding derivative of every component, so it's 0 and then 0. So component equal to 0, of course, the magnitude of it equal to 0. And that shows the magnitude of this, the curvature of this function is 0. Any question? Second derivative of the original function already equal to 0, of course, that make the curvature equal to 0. So you can see that the curvature is being impacted by the second derivative. If the second derivative of the original this function is all 0, of course, there's no chart. Back to that was the answer to the question. The t is the arc prime of s because we're using arclength parameter. And I'll have k x k equals 0. Okay. There's a jump between all the stuff we're doing. I feel like from here to here, there's a big jump. We had the key curvature defined as, this is our definition for the curvature, is the magnitude of t prime s. So we have to have parameter, arclength parameter s. However, how do we calculate it? We have parameter t. So for any random function, how do we calculate the curvature? This is the 3 different formula for the 3 different scenario. This part, I feel like the book has jumped in between those concepts. Number 1, if you have a function that is one-dimensional function, y equal to f of x, the calculation for the curvature equal to x value of the second derivative, as we mentioned, that the curvature will be affected by the second derivative. If the second derivative are all 0, of course, the curvature equals 0. So x value of the second derivative divided by the cube function of the magnitude of the derivative factor. So 1 squared plus f prime squared to the power 1/2. I think that's the magnitude of that's the arclength function that the calculation that we needed. The cube of that magnitude. So I feel like 1/2 is a magnitude. Try to compare with I'm trying to compare with a 2-dimensional and 3-dimensional version of the formula. Number 2, if you have a vector value function that is 2-dimensional, in that case, we will have 2 second derivative and 2 second derivative for the x and for the y. And here's the calculation. That's essentially the determinant for the derivative vector, if you think of it. Again, so I don't have the marker. I guess let's copy this. So whenever I want to talk about something here, put it on the board. It's many things to write. Okay, so basically what I mean is over here to make it easy to remember, you can think of this as vector, the first derivative vector. Okay, and the second derivative vector. Okay, and we take that as a 2x2 matrix, and these 2 multiply, subtract this 2 multiply. That's what you see in the literature. So that's essentially is a, you can think of it if you add a 0 to this, right? Add a 0 here, add a 0 here, add a 0 here. That's pretty much the cross product between these 2 vectors. That's what it is. So that's the magnitude for the cross product. And the denominator is, again, you take your first derivative vector. The magnitude of that will be square root of x prime squared plus y prime squared. That's this. This is the roots right there. So then you compute it. So the denominator essentially is cube of the first derivative vector's magnitude. Let's try to relate all three. In a sense, all three formula are slightly related to each other. So that was the two-dimensional formula. Numerator is the basically is the magnitude of the cross product between second derivative and second derivative and first derivative vector. And the denominator is a magnitude, a cube function of the magnitude for the first derivative vector. Lastly is the one that kind of combines things all together. I believe the third formula can be an indication of how the first and second formula are being derived. The last one saying the curvature calculation is essentially equal to, I would use this one, the magnitude of cross product between R prime and R double prime divided by the cube of the magnitude of the first derivative factor. So, there. Okay, and then you can also convert some relation. The first formula is T prime T, tangent vector T prime T divided by magnitude T prime T divided by magnitude R prime T. That formula is, again, I don't know if it's in the book, I think it's not. So if you want to look at the derivation of it, the last formula number 3, is a clue that connected 1 and 2. Essentially, the number 2 is a two-dimensional version of number 3, the cross product. That's that cross product part. And the denominator is a cube of the magnitude of first derivative magnitude. So these are essentially the same thing. And the top one, you can think of the derivative, the y equal to f of x as x f of x, the x f of x. You can think of it converted to a one-dimensional version or two-dimensional version, then that's derivative x, that's derivative y. So that's basically x prime square plus y prime square. So then you can match that with what we have is number 2. So essentially the number 3 is the one that connected all formula together. So I went ahead trying to think about a way to actually connect them. If this is the most important formula to remember and then connect all 3. And what would that formula come from? So I had a file that kind of explained things a little bit better. So here we are. I don't know if we have time to read the whole thing. So, but at least we have some source to convert. Not showing. So I have to open a new browser. It's a default file format. It's being read here. So this is really explaining the curvature formula. Where does it coming from? It started out with the same definition, curvature equal magnitude of dt, the derivative of tangent vector, if the parameter is s, and then that was the original definition. And when we also find out this is our definition for t, so using chain rule, we can have some. That's a k equal to 1 over a, the radius of the circle of curvature. We'll talk about that later. Now, there's a couple examples on all these calculations, and here we are. This is the one that is part of our formula sets. In here, it goes k equal to t prime magnitude divided by r prime magnitude. That first formula lead out to the third formula. So how do we get that formula? This is a mathematical proof of it. So in order to prove this, we have to study the chain rule. So dtt is, according to chain rule, is dt ds dSdt. dSdt equals r prime t as what we defined. So therefore, dt ds actually dt equals r prime t. Now dt, you want to find the magnitude of this to get curvature, therefore equal to this. So it's a simple enough proof for the first equation. And then the second equation is just go ahead and try to study how to find the t prime magnitude. So this is a little long-winded because we have to go ahead and find out how do we differentiate the t prime. And then the way we do it, we did it by product rule. So first you find a way to represent r prime. And then since we need, this is r prime, which is already being represented with multiplication. Right, R prime is the derivative of R, so the T prime is the direction, the DSCT is the magnitude of it. So if you want to find second derivative, you have to do product. Find product rule on R prime, you find this equation. That's where we have the summation because the product rule. And then what we're gonna do, we're gonna try to calculate the cross product, R prime and R double prime. In order to do this, we will multiply cross product R prime on both sides of this equation. That's how you get that one. And then the T is a unit vector. If you cross itself, the T cross T equal to 0, it has 0 magnitude. So then if you take magnitude of both side equation, this equal to this. So that's what we get this one. And then the ultimate purpose is kind of calculate the relation of the two. And then we can see this is our K. And this is our curvature. So this is basically how it's being divided. The magnitude of the T prime is the curvature. So the T prime magnitude equal to the cross product divided by R prime squared. Right. I didn't go. I can read through the whole file. It's a well-written proof of the curvature formula. The whole point for us is really to apply it. So we don't have to remember how to prove it. But just in case you wanted to know how to prove it, I want to explain that it's there. It's on Georgia. I want to find out the source of it, so it's available. All right. I don't want to spend too much time on the proof since we're not in a proof class. But you might be in the proof class later. So just want to show that it's there. All right, so we have a couple of work exercise on calculating the curvature. So the whole purpose for us is to be able to calculate the curvature, being in one-dimensional, two-dimensional, or three-dimensional case. Let's see. In the text, there's already a couple examples for each of these cases. In our homework, it has similar situation. So the first one is calculate the curvature of a circle with radius r. It serves two purposes. Number one, we will try to study the relation between that measure of the curvature and its relation with the radius r. So, and then another thing is we can practice using the two-dimensional version of the curvature calculation. Let's try to calculate curvature for this. Again, all these calculation questions, the solutions are already out. The whole thing is we know how to go about it, applying the formula to do it ourselves. So the formula for the curvature in conventional case is equal to, I don't know if you remember, absolute value of x prime multiplied by y double prime minus the x value second derivative multiplied by the derivative of the first derivative of y is the y component divided by the denominator. It is the magnitude of the derivative vector as squared. If you actually use parentheses instead of just known as square plus y prime squared. These are all derivative, not the degree 1 power. And then this is cubed. Right, so that's my way of representing the curvature formula. So we already have this, that's the x value, that's the y value. The only parameter is t. So we will differentiate x, that's going to be negative r cosine, r sine t, the root of cosine and sine. Maybe something will be better. Right, r sine t. That's the derivative of x. The derivative of y will be r cosine t. So then r cosine t has derivative of r sine t. So that will maybe it's easier just find the derivative first before we calculate it. So here is our function. The derivative, first derivative is equal to negative r sine t times the y component r cosine t. And then the second derivative is negative r cosine t. Derivative sine is cosine. Then the derivative r cosine is negative r sine t. So that's the derivative matrix. Like we said, the numerator is the determinant of the derivative matrix. So what you do, you're gonna multiply these two minus we multiply these two. So the calculation essentially is we multiply r with r, sine with sine. It's r squared times sine squared two plus we minus negative r squared cosine squared. So it ends up being a plus r squared cosine squared. Okay, so that's the numerator part. So cross product of the two factor, the derivative factor. So r squared factor out, cosine squared plus sine squared, which then equal 1. So the numerator is equal to r squared. It's now denominator. Denominator is supposed to be the magnitude of the derivative factor and then cubed. So here we have our c prime. The derivative is this one and that one. You square both, and that will be r squared sine squared plus r squared cosine squared, which equal to r squared, and then you take root. So the square root equal to r. So the denominator is essentially r cubed. Okay, so then this is really r squared over r cubed, which should equal to r1 over r. So that's our curvature. It's calculated by 1 over r. This is very interesting. We can see a negative reciprocal relation between the curvature and r. That is, the bigger the circle, whenever the radius is large, the smaller the curvature, right? Right? Even when we are walking on the road, we feel like we're walking straight. Supposedly the curvature is like almost 0, but we're walking on Earth, right? The Earth is a big circle. So, but this circle, the radius is so large, 1 over a really, really large circle, that makes the curvature small. So that we are almost like walking straight with the curvature is 0. So that kind of, well, this formula itself explains the negative reciprocal relation between curvature and radius. So that was a calculation in the book. If you want to see a more organized presentation, then this is what it is. But I wanted to write it from the scratch so we kind of see the process of going from the beginning. All right, so this is giving us the idea that the curvature value and the radius of the circle of the curvature has negative reciprocal relation. You can see on that original picture we're talking about at point B, if you're trying to fit a circle based on the curve presented in that small portion of the curve, you will be drawing a really, really big circle. So the curvature is 1 over the radius of that circle. Now, if you're trying to draw a circle at that turn at point A, we fix the circle with that circle. It's going to be a really small circle, which has a really small radius. 1 over a really small number give you a relatively larger curvature compared to B. Okay. So here the circle we're drawing has a name. It's called the circle of curvature or osculating circle. Let me just call them circle of curvature. And the radius is called the radius of curvature. So we can see from previous page that r equal to 1 over k curvature, or k equal to 1 over r. They are reciprocal of each other. And it's supposed to be, the curve is supposed to be tangent to the circle for it to be called a circle of curvature. Any questions? This is the definition for the circle of curvature. Hopefully we kind of see how it works with the example that we presented earlier. All right, so let's talk about the curve. For example, here we have a curve. It's defined by a problem. We want to find the curvature of y equal to x squared at x equal to 1. So with the curvature formula, we can calculate curvature of any graph at any point. Let's say about the problem. So if it's on, we go ahead and calculate. The one-dimensional case is easier because we don't have to worry about any matrices. All we have to do is to find the derivative. So this function, the first derivative equal to 2x. The second derivative equal to 2. Okay, so now the curvature calculation k equal to the numerator is supposed to be absolute value of the second derivative, okay, which divided by square root of 1 plus the square of the first derivative. Numerators are always about the first derivative. Numerator is a combination of the first derivative and second derivative. This is cubed. Right, so it's kind of related to the two-dimensional case, but not entirely, since we don't have to worry about the second derivative x, because first derivative x equal 1, second derivative equal 0, so the only thing we worry about is y. Second derivative equal to 2, so this is 2 over root of first derivative is 2x, so it's going to be 1 plus 2x squared. And then cube. So we'll plug in x equal to 1 here now. It's 2 over root of 1 plus 2 squared. And then cube. So it's 2 over what is it? Root of 5. Root of 5 cubed. Or you should write that as 5 root of 5. 2 over 5 root of 5. If we simplify this further, it's 2 over 25 multiplied by root of 5. And that we can probably calculate the curvature from there. Any question? Are we okay? Sure. All right, so that's the value of the curvature. It's not a big curvature. You can see the curvature is smaller than 1. And we can also calculate or draw the circle curvature. So that's a calculation. Oh, we were supposed to draw it at the vertex and at 0. And we draw at 1 point that's at x equal to 1. If you find the curvature at x equal to 0, this is going to be 0. So it's 2 over root of 1, which will be 1. So it's equal to 2. That's when x equal to 0. It's the curvature at 0.0. So we can have our solution. So x equal to 0, curvature equal to 2, x equal to 1, then curvature equal to 2 over 5 to the 3/3 power. So we have power. That's 0.179. So curvature is really small at 1, but really big at 0. So you can also draw the parabola. You can see at 0 is the curve, the biggest turn, and all the other points it's a small turn or almost no turn at a certain point. So that was the calculation. You can also calculate the circle of curvature, the radius of curvature with 1 over 2. That's the radius of curvature at 0, and then 1 over 0.179, which probably presents a bigger curvature. The curvature was 5.59. We calculate the 1 over 0.0179. That's the picture showing the circle of curvature. Any question? There's one more example, which should be a three-dimensional case. It will clear all the time. So the process will be calculating the first derivative vector, second derivative vector, and calculate its cross product. The difficulty of this kind of question is we used to calculate cross product, but it will be the first time the cross product include variables. So this cross product is a function actually. So whenever the t change, your cross product will change. So the calculation of curvature will be finding the cross product and finding the magnitude of it, just along a big calculation. And then we also have to find magnitude of the first derivative factor. And then again, you square every component and add it all together. You can see it's a big number as well. So this curvature calculation was t being the variable is long. So we will probably have to calculate individually for different t value. The question asked for finding the point where the curvature is biggest one. So this maximum value calculations are gonna be a little bit hard to find. The way we can find maximum value in calculus is to find the derivative. Find the derivative, set the derivative to 0, but it will be kind of difficult to determine. And set here, we will use a numerical solver. I'll see you tomorrow. That'll be our introduction to curvature today. Thank you today.
And that's one negative. Use negative. That's the same thing that are. There you go, negative. You know what was either.
And you can do every day. It's not on the body.
Exactly. That's funny, because like you see me take a position in grades, me taking this was to go down.
Being a slipper links for tomorrow.
Sure, yes. Do you want me to email it to you?
Yes, please.
Okay. Well, I can email you next, then tomorrow you don't have to wait for me to send it over.
Sorry.
It's the same thing every semester, so.
Okay. Thank you. Do you guys my email by any chance?
I have your email.
Okay. Yeah, take it.
Sorry. But I also always have a link on.
Okay,
Is it gonna like, leave?
the whole semester, the same way. Yeah, you can do it on your phone if you bookmark the link.
Yeah,
Mhm.
that'd be my email or links.
No, I know your name.
Okay, thank you.
See you tomorrow.
Yeah.
Or 11.
Sorry, I've been absent the past couple of days, but do you have any test one to return? Or would it be in your office?
That's fine. I think it's still in. Oh, it's in the office.
Okay.
Upstairs. I'll bring it tomorrow.
Okay.
Valid, right?
Yeah.
Okay.
Yeah, sorry I haven't been in class. I've been having some car trouble, but I've been attending virtually, so I'm still getting the notes and stuff.
Okay.
And then do you reopening 11.1?
I will. Is that?
Oh, okay.
Oh,
I'll ask you a quick question. Is there any way, so like you said next week, Thursday, is there any way we can finish that off? So I feel like I won't know the content, all of it by then. Well, I'm not confident.
Okay. But this section only has 5 session and we.
Is it
don't have
1.1?
one. So there's not a lot of.
What's it gonna cover?
It's all the problem on the homework sets.
Okay.
So if you're able to finish all your homework, I'll be ready. And we can go over those homework questions one by one in class if you have any questions. We'll try, and then if by Wednesday you feel like you still can't do it, and we'll talk about how many of us have did it the same way. It's possible to push it later.
Thank you. Thanks.